Hello, everyone. This is Michael Ferranti from Portworx, and thank you very much for joining our webinar today, Running Cassandra in Production on Kubernetes. Let's go ahead and get started. As I mentioned, my name is Michael. I'm VP of Product Marketing at Portworx, and I'm joined today by Janakiram MSV, Certified Kubernetes Application Developer, author, and analyst. We're very lucky to have Janakiram. He is an expert on all things Kubernetes, and you may have seen some of his writings in publications like the New Stack and in Forbes, and he's also a very sought-after speaker, so we're very lucky to have him with us today. The topic of our webinar today is running Cassandra on Kubernetes in production. And let me just say a word about in production. A lot of information on the internet around running stateful services like Cassandra and containers focuses on what we call day one operations, deployment and configuration. And that's very important, but it doesn't get you all the way to a real production deployment of a critical application like Cassandra. So what we're going to do today is really spend some time focusing on those day two operations, things like how do you keep your app up and running when a server fails, or if you're out of space. We want to make sure that we really dig into those topics so that you understand not just how to get started, but actually run the app in production. Okay, so to get started, the first slide I always like to share is some of the customers using Portworx in production. And the reason I show this is just to let you know that whatever industry you're coming to containers from, kind of whatever your deployment target, whether that is public cloud or private cloud or multi-cloud or hybrid cloud, Portworx has customers that are doing exactly that. As you think through the key problems that you're trying to solve, we can bring that experience to bear directly on your problem. So what is Portworx? At a very, very high level, Portworx is a distributed block storage solution that deeply integrates with any scheduler, including Kubernetes, to run and manage any stateful service. Today's webinar is about Cassandra, but that includes Redis, that includes MongoDB, Kafka, Postgres, MySQL, and any other stateful service that runs on Linux. In any cloud or on-premise data center or across all of these environments, in clusters of up to 1,000 nodes each. So Portworx itself scales to the same levels that we see Kubernetes scaling to. Okay, so the topic of today's webinar is Cassandra in production on Kubernetes. So let's dive right into that. I'm going to spend about 3 more minutes giving an intro, and then I'm going to turn it directly over to Janakiram, who has a live demo for us. So let's look at saying, okay, we want to run highly performant and resilient Cassandra cluster on Kubernetes. How do we do that? Well, the first thing we need to do is make sure that we install Portworx on our Kubernetes cluster. Portworx was designed from the ground up, not only to provide persistent storage and data management to containerized applications like Cassandra, but also to be run and managed itself as a container. So installing Portworx is as easy as kubectl apply-f and a YAML file that we help you generate directly from a web interface. Once we've done that, we can actually start using kubectl to configure and deploy our Cassandra cluster. The first thing I'm going to do is create a text file, a YAML file called a storage class. Here I'm highlighting an important a feature of storage class, which is replication factor. How many copies of my data volumes do I want Portworx to maintain at all times? But this storage class is very powerful because it can also include things like what type of storage resources do I want provision for my Cassandra cluster? Do I want, say, an I/O priority of high or an I/O priority of low that might correspond to, say, an SSD or an HHD, or from an Amazon might correspond to an EBS volume that has dedicated IOPS or something like that. I could also include snapshot policies, other policies that I would want uniformly applied to my Cassandra database from an operations perspective. So once I have that storage class, then I am going to create another file called a persistent volume claim, which will reference that storage class. And then I can create my deployment again within Kubernetes. And all of a sudden, I have a multi-node Cassandra cluster deployed using Kubernetes and with persistent volumes provisioned by Portworx. Now, something really important to mention here about Cassandra specifically, which is that Cassandra likes to be deployed using a model called the network topology strategy, which means that it says place your Cassandra workers across failure zones within your data center. That means that if I lose one of my nodes in one failure zone, I still have my other nodes in the other failure zone, giving you a certain level of high availability. This is quite complicated to take on manually, especially when you're running multiple Cassandra databases per host, as many of our platform as a service customers do from a density perspective. So Portworx places your data volumes automatically across failure zones, giving you that first level of high availability. What we do additionally, because we set a replication factor in our storage class, we are also going to deploy replicas of your data volumes to other hosts in your cluster. So now if we lose a node, rather than rebuilding from scratch, we can simply fail over to another host in our cluster that already has an up-to-date copy of the data. Portworx actually tells Kubernetes which host it should reschedule that pod on, making sure that the data is available and you maintain hyperconvergence. And you also don't suffer the decreased performance that comes as Cassandra tries to rebuild one of its workers from index on other worker nodes. Additionally, Portworx provides a feature called Cloud Snap, which is very, very helpful when it comes to offsite backup. So imagine I have a Cassandra cluster running on premise. I want to have a backup cluster running in the cloud. I can snapshot those volumes, send it to any S3 compatible object store. In this case, I'm saying I'm going to send it to a Minio cluster, but this could be S3 or it could be Azure file storage or file storage on Google. And then I can restore that into the cloud. We also support bring your own key encryption. Oftentimes Cassandra is used for really, really sensitive data. And it's important that only you are ever able to access that data. So we support kind of the leading encryption solutions like HashiCorp Vault. And again, only you are able to decrypt that data. Portworx even doesn't have a key. And with that, I'm going to turn it over to Janakiram, who's going to walk us through a demo of a lot of these production features in more detail. Janakiram, over to you.
Thanks, Michael. So that was a quick walkthrough of the capabilities of Portworx. So let's actually take a closer look at some of these features. So as Michael mentioned, the entire use case is revolving around Cassandra. And there are 3 steps that I'm going to walk you through. The first one is deploying a stateful set based on Portworx volume. I'm going to do a very quick walkthrough of what is a stateful set and how can we deploy a stateful set on the storage cluster running Portworx. That's the first step. The second step is we are going to do a failover. So we're going to deliberately knock off one of the nodes and see actually what happens to the data. And as Kubernetes recopes with it and as stateful set creates another pod, we are going to see how the data is going to get recreated. Now, the third step is very interesting. I'm going to introduce a concept called 3D snap, which is very apt for sensitive, highly available clusters like Cassandra. So let me get started with the very first step. So at this point, I have a simple 3-node cluster running in EKS, but this doesn't really matter. You can run Portworx on any Kubernetes cluster deployed anywhere, any cloud of your choice, on-prem, doesn't matter. So that's the 3-node cluster, and we also have Portworx running within the EKS cluster. And since Portworx always runs as a daemon set, we see that there are 3 pods assigned to each of the nodes. So this is the environment that we have. The very first thing that I'm going to do is to deploy a storage class. And as Michael mentioned earlier, a storage class is going to be the interface between the app and the Kubernetes storage engine. In this case, it is Portworx. So a storage class in Portworx is a lot like the profiles in traditional storage environments like SAN and NAS. So here we're going to define a profile with file system, the replication factor, the throughput parameters, and many other configuration settings that actually define how this profile is going to deliver to the workload that we are running. So in this case, I kept it very simple. I have omitted most of the settings except what is called as the replication factor. And here you notice that the replication factor is 3, which means anytime we write data to any of the nodes, it automatically gets replicated to at least other 2. So at any given point of time, we have data available on the current node where the data is being written, plus 2 more nodes, which is going to maintain the redundancy. So let's get started with the storage class. So I'm going to create the storage class, and this would result in a new storage class that we exclusively created with replication factor 3. So when we do a kubectl get storage class, we notice that the px storage class is now available to us. That's the foundation. That's the very first step on which we are going to launch the workload. And Cassandra as a stateful set has some unique attributes. So this is definitely not a crash course on stateful sets, but in case you're not familiar, a stateful set is a controller on Kubernetes that brings the capabilities of a replication controller to stateful pods and stateful workloads. So when you launch a MongoDB cluster or a Cassandra cluster or a MySQL master slave, you need certain attributes like the host name got to be fixed, and you need to create a high affinity between the node, the storage, and the workload. So all those capabilities are delivered by the stateful set. And the best thing is, like a replication controller, you can actually delete one of the pods in the stateful set, and it automatically recreates, assuming you have a storage layer that is capable of handling the recreation and the failures at the pod level. So one of the requirements for a stateful set is to create what is called as a headless service. And this headless service is going to facilitate communication across all the nodes of our cluster. In this case, all the Cassandra cluster, nodes of the cluster will talk to each other through the headless service. So the headless service is called headless because we don't assign any IP address to it. So this is how a headless service looks like. Instead of giving the type as cluster IP or node port or load balancer, we actually say cluster IP is none. In this case, we only have the service exposed to the pods of the Cassandra stateful set for internal communication. So this is a prerequisite and a mandatory headless service that we need to have before we create the Cassandra cluster. So let's create the service, and this is going to result in the headless service that I just mentioned. So once this is in place, there we go. So this is a cluster IP with no IP address assigned. Now it's time for us to go ahead and actually create the Cassandra stateful set. So let's take a look at the definition. So this is a standard stateful set. If you have seen the definition, the YAML definition in any of these scenarios for MongoDB or MySQL or any of the workloads, this is not very different. Except that we have a couple of annotations and a couple of special mentions. The first thing is you would notice that the scheduler is not the default Kubernetes scheduler, but we are using what is called as Stork, which stands for the storage orchestrator for Kubernetes. And this is responsible for ensuring that a pod that belongs to the workload is always placed where the data is. So in a scenario where you have multiple nodes, but a few of them are assigned to run stateful workloads backed by SSDs and high throughput, high IO volumes, you don't want the pods to get scheduled on nodes where there is no backend or no high performance storage. So that will result in a very strange scenario where data is corrupted and you have very inconsistent results. So what Stork will ensure is anytime a pod is rescheduled, it will always go to the node where the data is available. And that is the job of a custom scheduler. And Stork is one of the custom schedulers deployed by Portworx within Kubernetes. So we mentioned the scheduler as Stork to make sure that we have the hyper-converged infrastructure where the data compute, that is storage compute, and the application are running on the same node each time and every time. So that is the scheduler. And then when we create the volume claim template, we actually mention that this is based on Cassandra data. And if you notice, the mount path is also very specific to Cassandra. This is where the persistent data is always written. And this mount point is basically backed by Cassandra data volume, which is pointing to the storage class that we created in the previous step. So this is how it all gets connected. So when the stateful set gets created, it looks up for this mount path. This mount path in turn is based on the storage class that we created in the previous step. So let's go ahead and create the stateful set. This is going to take a minute or two. So let me split my screen because I'm going to show you two things at a time. So let me go ahead and launch the Cassandra app, which is nothing but a stateful set. While this is going on, I want to put the pod creation in watch mode so that we know how the pods are getting created. And at the same time, I also want to show you a concept called the dynamic provisioning. So now we'll actually notice that there is a new PVC that is getting created. It's going to be in pending state for a few seconds because a dynamic volume is going to get created and it gets bound. And there we go. Now we notice that this is actually bound to the first pod that's launched as a part of stateful set. So it's in running mode, which is a great relief because sometimes this can really go wrong and you have to debug why this is happening. So in this case, the first PVC is created and it is immediately bound to the first pod. And now we are almost at the last step where the third pod is also getting created, and all the three should be in running mode in a few seconds. And this is an indication that everything has been good so far. In the sense that the storage class has been created successfully, the headless service is in place, the Cassandra stateful set is created, and the dynamic volumes are also created, which are bound to each of the pods that are created. And now we are done with the creation of the stateful set. If you are curious to know more about the actual creation and the YAML definition, there is actually a tutorial that we published recently. You can look up the tutorial for all the details. Now that the stateful set is in place, let's inspect the environment a little bit. So now I'm actually trying to get one of the pods of the Portworx daemon set. So when we actually execute this, the environment variable called pxpod will be pointing to one of the pods of the Portworx daemon set. We need this because we want to execute a utility called pxcuttle. So with the pod name available to us, I'm going to execute this command, which is going to run within the pod of Portworx daemon set. And we are invoking this nifty tool called pxcuttle, where we are listing down all the volumes. So V is the volume, L is the alias for list. So this is going to show us a lot of interesting, insightful information. Basically, we see that there are 3 volumes that are created by Portworx, of course, through the Kubernetes interface. And all the 3 are green. They are up and running. Each of them are of 5 GB size. And they are highly available because we set the replication factor as 3. And this is another great indication that everything has been executed the way it is expected, and the cluster is now ready for production workloads. Finally, we can also take a closer look at one of the volumes responsible for running the PVCs. So now I'm actually grabbing the volume that is associated with one of the stateful sets, which is Cassandra 0, the first one. And then we can now, again, get the name of the Portworx pod and then inspect one of the volumes, essentially the PVC that is bound to pod 1. is going to be inspected, and this will show us much more closer, insightful information on the current status. So this is just one of the volumes out of the three. The size is 5 GB, the file system is ext4, the HA mode is currently 3, which is replication factor. There are some labels. PVC is Cassandra data, Cassandra 0. This is very essential. I'm going to touch upon this later when we talk about 3D snaps. And this volume is now is available to replica sets across these three nodes, and it is currently controlled by the Cassandra stateful set. So this is again a very useful diagnostic information about the current status of our deployment. So this is not really day 2, this is almost day 1, where we go ahead and configure Cassandra on top of Portworx. But as you start performing DBA operations and storage ops, things turn pretty interesting. So now let's move to day 2 and perform some routine operations, but in the context of container native and cloud native. So that ends my first demo. Let me start with the second. So here what we're going to do now is to inspect the Cassandra environment through this native tool called node tool. So this is going to show us the current node distribution and the utilization factor. So currently we see that there are 3 nodes, and if you are already familiar with Cassandra, you identify with this because this is a very routine step that Cassandra DBS perform to explore the current status of the cluster. So this actually shows us that the data, or rather the cluster, is distributed across 3 different nodes, and this is the distribution factor, and these are the host IDs of the nodes within the cluster. So Cassandra follows a ring topology where we have multiple, at least 3 nodes as a quorum is deployed across multiple availability zones or failure zones, so that if one of the nodes faces a disruption or a failure, the other 2 will automatically start serving, and you can bring back the third node without losing any data. So that is the topology of Cassandra. You can also figure out the mapping between Cassandra and the pods. So I'm using JQ, which is the JavaScript query tool for the command line. In fact, it is more of a JSON query tool. And what this is going to show us is the association of the pod IP with the host IP and the host name of the node. So this is again another view of the cluster with a one-on-one mapping between each node of Cassandra with the host name of the node, and then the host IP and the pod IP. So this again gives us a good understanding of the topology. All right, so now I'm going to get onto the SQL SH, which is the Cassandra query shell, and this is going to drop us into the Cassandra environment. And what we'll actually do is to populate the Cassandra database with some sample data. So first I'm going to create a new key space called classic models, and this is going to have the consistency quorum, which is every time the data is written, it's automatically distributed across all the nodes participating in the quorum. Then we use the database that we just created, and then we run a bunch of DDL statements to populate this. So now I'm creating a table called offices, and this is going to have some sample data that we're going to populate. So let me get all of them together and run them. So we're going to have about 8 rows just to make sure we have some decent amount of data populated in the sample database. And let me verify whether the data is created. Oops. Okay, so there we go. We have this grid that actually shows the populated data. So now we are in day 2 operation where the businesses started to populate their respective databases, tables, and applications are reading and writing from this backend. So now let's actually do a failover. So for that, we need to basically simulate one of the node failures. So what we'll actually do is, let's take a look at the current set of nodes. If you remember, I said there are 3 nodes running on EKS. Now, what I'm going to do is to grab the name of the node that's running the first part of the Cassandra stateful set. So when we do an echo of node, we notice that obviously this node is running Cassandra 0 pod. So now what I'm going to do is to cordon off the node. So if you're familiar with the cordoning concept, what it basically means is it will disable scheduling on this node. And what this means is subsequent pod creation will not result in creation of a pod on this node. So basically, this is a flag to the Kubernetes scheduler and controller saying this node is alive, but not ready for scheduling. And all the current pods continue to run, but no new pods can be scheduled on this node. This is very useful when you want to perform upgrades or maintenance tasks, or temporarily pause scheduling newer pods on this so that you can basically debug, fix, and bring it back online whenever it's ready. So we are actually simulating a node failure by playing it safe, and we are running kubectl cordon. So once we run this, basically this node becomes unavailable only in the context of scheduling. So now when we actually do kubectl get nodes, we notice that scheduling is disabled on the second node. Now what we'll actually do is to go ahead and delete the pod that's currently scheduled on this. So when we actually look at the current pods, there are 3 pods running, and all the 3 are basically mapped to one of the nodes of the Cassandra cluster, and it's a part of the stateful set. Remember, cordoning of a node doesn't result in deleting existing pods. So even though we have cordoned off the node, the Cassandra 0 pod is still running. So now what we're going to do is actually delete that pod that is currently scheduled in one of the cordon nodes. And this will result in 2 things. One, telling the Kubernetes controller to knock off this pod. But because it's a part of stateful set, and we have 3 nodes defined as a part of the stateful set replica, it is immediately going to result in creation of a new pod. Now, this pod has to be relocated to one of the other nodes, and that should actually be running the Portworx storage layer, and the data should be available. That's where Stark kicks in and ensures that the pod is not placed in any other stray node that doesn't have the data and doesn't have the storage fabric, but instead it gracefully routes the pod to one of the nodes that actually holds the data which belongs to that specific workload. So now let's go ahead and delete this pod, and immediately we see that Cassandra 0 gets terminated and a new pod shows up. So that's going to take just a minute, but as soon as, there we go, it is terminated, and now the container is getting created, and now it's back in running mode. And the node is still in a cordoned off mode, which means no new pods can be scheduled. So we have just simulated a node failure and recreated it. So let's see if the data is still available. So at this point, what I'm going to do is to run the same select query that we ran earlier to check if the data is still intact. So now I'm going to invoke the select start from classic models.offices on the same pod that we actually deleted. And beautiful, the data is still there. It is effortless, and we really didn't do anything that is very specific to retain the data. It is the magic of Stark and Portworx, which is ensuring that the pod of the stateful set is always placed on the same node where the data is available. And it is automatically mapped to the original volume that was serving Cassandra 0. So this is a complete walkthrough of the failover. Before I go any further, let me make sure we uncordon the node to avoid any unwanted issues later. So now we are back to the normal topology, normal scenario where we have 3 nodes and all of them are ready for scheduling. So that was basically the second demo where I have walked you through the failover of one of the Cassandra nodes and how we gracefully brought it back with zero downtime and zero disruption. All right. So now I'm going to walk you through the last and final step of this demo, which is very interesting. Now, if you are familiar with block storage in any of the cloud providers like AWS or Azure or Google, you appreciate the concept of a snapshot. So snapshot is very critical for running workloads backed by block storage. Particularly on EBS, a lot of customers run cron jobs to make sure that they take periodic snapshots of the EBS volumes, store it in S3, and whenever there is a failure, they can easily restore the snapshot to an EBS volume, attach it back to another VM, and boom, the application is back online. Now, applying the same workflow and same use case to container native storage is not easy. It's not straightforward. And it becomes more critical when you are running very sensitive, very high IO, high throughput, highly transactional database like Cassandra. Now, even though you are able to take snapshots, the challenge is you have a distributed cluster where data is simultaneously and parallelly written across multiple nodes. So when you're taking a snapshot on one of the nodes, the other node might end up writing data which will result in very inconsistent snapshots and inconsistent backup. And that is going to defy the whole purpose of creating a snapshot from a running application. So some of the advanced scenarios actually implement a concept where just before you take a snapshot, you basically do a flush or you perform a locking so that no new records are written. And then you initiate the snapshot. And as soon as the snapshot is over, you unlock the database so that the write operations can resume. Now, how do we do that with container native storage? Well, Portworx has an extension of the snapshot framework, which is now called as 3D Snap. So 3D Snap is a very consistent way of taking snapshots, particularly in distributed environments like MySQL master slave or MongoDB replica sets or Cassandra clusters. It is called 3D Snap because there are three dimensions to the backup that we are performing. The first one is, of course, time. So it takes timestamp into consideration. The second one is the node, which is basically the space, the storage. And the third one is application. So when you combine these three dimensions in an access, and when you perform a very consistent snapshot, what you actually end up getting is called as a 3D snap. And this is highly consistent, doesn't leave any transactions in limbo. It actually considers the fact that it's a distributed cluster with distributed reads and writes, and anything can go wrong. But how can this be generic? It is not specific to Cassandra. It is not specific to MongoDB or MySQL. So to enable DBAs and storage admins to do what is appropriate for their workload, 3D Snap gives you what is called as the post and pre-snap triggers. So just before you initiate a snapshot, you can run a rule which might be something like lock the database before the snapshot starts, perform the snapshot, and after the snapshot is over, unlock the database. So you can create a rule that is going to trigger just before the snapshot is initiated and right after the snapshot is completed. And what you do with the rule and what you do with the trigger is completely up to you. It could be calling one of the database specific commands, or it could be running a script which will flush everything to the disk and then initiates it. So it's completely up to you. So now what I'm going to demonstrate is a 3D snap performed on Cassandra. So the very first step that we're going to do is to create a rule. And why do we need to create a rule? Because before we initiate a snapshot, we want to make sure that all the nodes participating in the Cassandra cluster flush the database, flush the data from the mem tables. So we actually create a rule, and this is very, very specific to Cassandra. So here the type is command, and the actual value of this is node tool flush, which will make sure that data is flushed out of the mem tables to the disk. And this is going to be executed on all the three nodes of the Cassandra cluster, making sure that there are no transactions in limbo and we are not taking corrupt inconsistent snapshots at that given point of time. So the very first step is to create a rule. So let's go ahead and create this rule. All right, and if you're wondering when does Kubernetes start to support rules and what does it really mean to Kubernetes? Well, this is not really a Kubernetes native object. This is called as a custom resource definition. It's a CRD created exclusively by Portworx. And this is based on the definition, which is called the rule. So it's a CRD. If you're familiar with CRDs, you can relate to it because it's going to give us very familiar operations on custom types like rules. So we have now created a new rule. So when you actually say kubectl get rules, we see the rule that we just created, which is the Cassandra rule. So with the rule in place, now we are going to create the actual snapshot. And creating a snapshot is not very different. Here, this is the snapshot definition, and this is a standard Kubernetes volume snapshot object definition. Nothing different, or we are not deviating from the standard spec, except that we introduce a couple of very interesting and very important annotations. And these annotations are safely ignored by Kubernetes clusters that do not run the latest version of Stark or do not understand what a rule is. So these annotations are they light up when you run in the context of Portworx running a specific version of Stark that can understand 3D snaps. Otherwise, this doesn't really matter. It is like a comment that Kubernetes will safely ignore. But here, we actually mention that the app is Cassandra. And where does this point to? Well, when we actually created the app, you will notice that in the PVC, I mentioned the app as Cassandra. And this label is going to be associated with our snapshot. So this is the basic indicator which is going to match the snapshot with all the PVCs that match the label. And then we're also mentioning the pre-snapshot rule is the Cassandra rule that we just created in the previous step, which means before you take a snapshot, please run node tool flush for me is what this YAML file will tell Kubernetes. And we are also giving the Cassandra PVC name, and because it's a 3D snap, we can just point it to one of the PVCs. If you notice, we are not mentioning Cassandra 1 and 2. It's not really required because we are using an app consistent snapshot, and we are giving the label, which means this label is going to do a filter on all the PVCs that match this criterion, and automatically it's going to perform. This is just a standard placeholder that we need to use to make this definition look complete. But the actual magic happens with these two annotations that are very specific to Portworx. All right, so now it's time for us to create the 3D snap. So let's go ahead and kick off that job. So now as soon as I run this, Portworx will receive this request, and immediately it will coordinate with the CRD that we created in the previous step. And this is going to result in not one snapshot, but 4 snapshots. And why do we need to have 4? Well, the first one is the default snapshot that Kubernetes is aware of and deals with. But the remaining 3 are very specific to the 3D snap and are managed by the Portworx environment. And this is not really what Kubernetes natively manages. So that's the reason why we see 4. The first one that is very specific to Kubernetes, and remaining 3 are a part of the 3D snap. Now, this is, again, a good indicator that the 3D snap has been successfully processed, and now it is in place. All right, so now we have taken the snapshot, and I'm going to do something pretty crazy. I'm actually going to delete the stateful set that we have. So let's keep this in watch mode, and then I'm going to go ahead and delete the entire stateful set. And this is actually very scary because we are now tampering with the production database, and we're actually deleting all the pods that belong to this workload. But we need not worry because we have a 3D snap, and in a few minutes, I'm going to show you how I can basically restore not just one node or one volume, but an app consistent restoration across all the nodes that belong to this workload. All right. So now I'm also going to delete all the PVCs because we're going to recreate the PVCs. So currently we have 3 PVCs from the previous step. If you remember, when we created the stateful set, it resulted in the creation and binding of 3 PVCs to the pods. Unfortunately, when we delete a stateful set, Kubernetes doesn't delete the associated PVCs. So we need to manually do that. So here I'm taking advantage of the labeling. So I'm saying, go ahead and delete all the PVCs where the label is Cassandra, app is equal to Cassandra. So this is going to delete all the 3 PVCs. So now we are actually sitting on a blank slate. We don't have any pods, we don't have any PVCs, and our cluster is as good as brand new. So we don't have anything at this point. Now, what we'll actually do is, from the snapshot that we have taken, we are going to recreate the 3 PVCs manually. And this step is going to get better with some of the upcoming versions of Portworx. But at this point, we got to create these PVCs manually. Now, what we're actually doing here is taking advantage of the naming convention of a Kubernetes stateful set. So now we are actually creating 3 PVCs manually from the snapshot. So if you notice, this is Cassandra 0, and we are actually asking the Stork and the CRD to restore it from one of the volume snapshots that we created earlier. So now what we'll actually do is to get the volume snapshot, right? And carefully place this in our definition. So we are now recreating the broken and deleted volumes with this. And let me also do the same thing with the remaining 2 PVCs. We are reconstructing everything that is lost. And this step is slightly manual, but I'm very sure this is going to become better with the upcoming versions of Portworx. So now, oops, let me first get rid of this. We don't need to put this in watch mode. It refreshes very often. So let me grab the second volume snapshot ID and place it here. Finally, we're going to repeat this step for the last and the third one. So if you notice, everything is same except the arbitrary index, which is basically associated with the stateful set, is changing, but I want to make sure I don't miss anything. So I'm basically grabbing the entire string and pasting it here. All right. So now we have 3 new PVC definitions, and these PVC definitions look very similar to the conventional standard definitions, except that we have an annotation. And this annotation is a hint to Stork to basically create PVCs not from the blank volume, but as a part of the restoration process from snapshot. So with these 3 in place, let me run the command. So now we are actually going to create the first PVC, then we're going to create the second PVC and the third one. So now this step, oops, sorry, it must be 2. So now this step will result in 3 PVCs that we originally deleted, and they are almost looking very similar. They are exactly how we basically saw them just before we deleted. So now what we'll actually do is to come back and launch our stateful set. And this is Cassandra app.yaml. No changes to the stateful set. It remains exactly the same, except that we are now pointing it to the pre-configured, pre-populated PVCs that we manually created. So now we'll go ahead and launch the stateful set, and in a few seconds we should actually see that the entire stateful set lights up and all the 3 pods move to the running mode. So let's give it a few minutes. So in the interest of time, I'm going to wrap this up. It's not very different. Finally, what's going to happen is once the stateful set comes back, and because it is mounted on the pre-configured, pre-populated PVCs, we'll be able to query. So so that is the end of this demo. And before we move to the Q&A, I want to bring up a couple of polls.